Hi there, guys. So in 9F, we dealt with transition state diagrams, which came from Markov chains of probabilities which were dependent on a previous outcome to an event. And then from the transition state diagrams, we developed transition matrices. So that's in the previous video. And in 9G, we're talking about applying these matrices many times over to a particular starting state, so a particular initial state vector. Now, we're also only going to be dealing with regular transition matrices, which means to say that we'll end up with a steady state vector at the end as well. Okay, so practically, let's have a look at a question first, and then let's go back to a bit of the detail as well. Okay, so this is the question, the example question, which is taken from 9F, but it's now in 9G as well, and they're developing it on further. And so we've still got this dockless bicycle company, Math Bike, and they still have their 3 locations. They have, let's just go back to that again. They have, so same thing as this, okay? So they have the central, the zone, the, what do they call it? Central, and the inner zone and the outer zone. Okay, so these are the 3 locations. This is the current location on this side. This is the ultimate location where they're going to end up at the end of the day. Now, in this example, we also looked at the probabilities of where the bikes end up after multiple days. So if you apply this matrix, say, for example, to the power of 3, then you'll get out probabilities which show you where the bicycles are likely to end up after 3 days. So that was this thing here. Now, what we're going to do in 9G is we're going to raise this to the power of maybe 50, or potentially to the power of a very high power here to see what we're tending towards. Okay, so, and we're going to apply this as well to a particular initial vector. So again, let's have a look at this thing here. Okay, so this one says a dockless bicycle company, back to that one again. And it says there's an initial state vector here. So our initial state vector, we can call S0. So if you want to write that down in bold, for us, that's going to be S underlined 0. And so this is going to be how we start. So this is going to be 110 bicycles in the central zone. This is in the inner zone, 80 bicycles, and there are 50 bicycles in the outer zone to start off with. Okay, so first question says, calculate the likely number of bicycles in each zone after the city, in each zone of the city after 5 days using the transition matrix given in example 10. So here was the previous transition matrix. We apply that 5 times over to this particular vector here. And you can do this just straight on your calculator, and we end up with these numbers here. Okay, so that's after 5 days. And obviously, you're going to need to make some sense of this. It says calculate the likely number of bicycles. So you can say, well, okay, this looks like 66 bicycles. This looks like 76, and this looks like 98. So I'm just rounding off there. Now, potentially, there's an issue there if your numbers don't add up to the same total, and in which case you'd have to see which one is perhaps nearer to the middle when we're rounding off. So say, for example, this was 65.9 and this was 75.6. You might want to keep this one at 75 and you might want to go up to 66 on this one. So, you know, you don't want to end up with more bicycles, and it just and you just need to check that. That's just a little extra thing to check there. Just checking, this one should end in a 0. So 6 and 6, 12 plus the 8 is 20. So it's going to end in a 0. So I can see that one checks. That's okay. Okay, then it says find the steady state of the mass spikes. So steady state means over a long period of time. Now, we are only dealing with regular transition matrices. Now, what that means is that these will always converge when you apply to a vector, to a particular initial vector, you will always converge to this steady state or this stabilized system. So there's no kind of oscillation, and this is because we're always dealing with regular transition matrices. Now, irregular transition matrices are beyond the course. So we're always going to end up with this situation. Now, in terms of regular transition matrices, when you apply them to, say, a very high power, you'll notice that each of the columns will be the same. So for example, the first column might be 0.5, 0.3, 0.2. Then each of the next columns will be the same. So it doesn't mean to say that this will be a third, a third, a third. It means that whatever you have in the first column will be in the second, will be in the third, and you apply it many times over. Okay, now we'll look back through the book just to clarify those points in a bit, but let's deal with this question first. So find the steady state of the mass spikes. So obviously you can't put in infinity into your calculator, so you just want to choose a high number. And these are likely to converge within a matter of tens. You could perhaps try 100 on here. I think in the book they try 50. Okay, so let's just go forward to this one. Okay, so they try 50. So they're just trying a high number here. And now when they've tried a high number of 50, they see that the results are actually really similar to the previous results. So again, here we can see, so we know if after 50 goes, it's very similar to after 5 goes, we know that we've approached some steady state. Now, if you're not convinced by this, by just choosing a large number, you can always try 100 and see that you get the same numbers which are rounding off as well. But obviously you can't choose infinity, and frankly, I don't know, maybe your calculator will be extremely slow if you chose 1,000, for example. But you could try 50, you could go back and try 100 and just check that the numbers are the same there. Okay, so we can see in this case we're getting 65, 76, and 99. And again, that is adding up to the correct number of bicycles in the system. So since these two are very similar, we're pretty content that doing it 50 times is good enough. Okay, so the system quickly reaches the equilibrium at 65, 76, and 99 in each of the zones. Okay. Yeah, so as it says the rate of conversion depends on the values you are given. It depends on the matrix that you're given and the values you're given to start off with, of course. Okay, so finally in this question it says, comment on how the owners of math bikes should reflect on their choice of initial state vector, state the limitations of this model. Okay, well, I mean, you can come up with any sensible choice of things here. Now, it looks to me like they should have put 65 in the central district to start off with, and then 76 here, and then 99 here, because obviously there had to have been it was slightly incorrect to start off with, and then after time we find it's approaching this steady state, this system which is working well. Now that's often not the case in these systems. Often you have to take bicycles from one area at the end of the day to another area because there's certain patterns that people follow. But again, we're dealing with regular transition matrices here, where we end up with an equilibrium state, a steady state vector, or a stabilized system. Okay, so comments that they're saying to the answer of how they should reflect. Yeah, I think they say they would have met the needs of the customers better by placing the 50 bikes here and the 150 bikes here. Perhaps, yeah. I mean, otherwise you could have actually put exactly these bikes in the certain areas if they knew these probabilities to be true in the first place. Okay, and it also says the model does not account for broken or stolen bikes, nor does it account for the changing habits amongst the customers due to weather patterns or competition from other companies, and potentially the changing in the daily habits as well. I mean, for example, on a midweek day, you might have a lot of work commuters, and on a weekend you might have a lot of leisure commuters. So you might find that the movements of bicycles and the probabilities, the Markov probabilities, the Markov chains, depend on whether we're dealing with a weekend day or a weekday, and that would make the model more sophisticated. Okay, guys, so I'm now going to go back through some of the theory here. Now we've dealt with that question. Obviously, if you're feeling confident, you can have a go at some of the exercise 9H, but I'm just going to go back through some theory because there's a lot of these little boxes in the book, and I want to make some sense of these ones as well. So let's go back through to here. It starts off with 9.6. It says represent steady state systems. We're talking about a matrix, normal transition matrix, which is going to be a square matrix in our case. Now, there's nothing particularly interesting there. This is just saying that we can apply our transition matrix n times over. Okay, now in particular, I wanted to deal with this again, just to repeat this statement here, because this was pretty important. Okay, so it deals with the fact that we've got regular transition matrices, and we're not dealing with irregular ones. And it says has the property such that there exists an n belonging to your positive integers or your natural numbers starting from 1, such that all entries in t to the n are greater than 0. Think about what that means. That would mean that you don't have any zeros in this matrix here. And for higher powers of n, a regular transition matrix converges to a matrix in which all of the columns have the same values. So again, remember what we're saying, that could be 0.5, 0.3, 0.2. Remember, this needs to sum to 1. And then each of the columns would be the same there. And we will only deal with these regular transition matrices. And remember, I also talked about steady state. Now, this t to the n, so if we've got our regular matrix t, our t to the n will end up having the columns being the same, but that's not our steady state, or at least I'm not our steady state vector. That's just simply our regular transition matrix applied n times over. Okay, now if we apply that vector, sorry, that matrix, so let's apply this matrix to our Sn, if you like. So we're talking about our steady state vector at the end, like for example our bicycles at the end being whatever it was, 68, 95 or whatever, that steady state vector. If we apply one more time, after we've applied this n times, okay, if you apply it one more time, you should get the same answer again. Okay, and if you apply t to the n to S0, okay, our steady state vector, then this should tend towards S to the n as n tends to infinity as well. Okay, so we're kind of saying the same thing in two different ways there. So if we apply t to the n to our initial state vector, many times over, we will tend towards our steady state vector, then becomes larger. And if we already have our steady state vector, then when we apply t one more time, we should continue to get our steady state vector, as long as we have a regular transition matrix. Now, what I'm talking about there is another box which is given. Talk about initial state vector. There's another example in the book here. I'm not going through. And what I was talking about there is this, and they're calling the matrix now P, but I've called it T. If P is square regular transition matrix, there is a unique vector, and I'm calling that the steady state vector, such that when you apply T to the steady state vector, or PQ, you continue to get Q. And Q is called the steady state vector. So all I'm doing there is just unpacking what I've just talked about and that extra box there, when they come up with that extra box, putting P and Q, giving Q, is the same as this thing here. Now, by the way, I've put underlines underneath these because they're bold when they're given to you. So if you're defining your matrix, you can always put an underline underneath the capital letter, and that will just denote that we've got a bold letter, but we obviously find that difficult to do ourselves. In terms of the exams, it doesn't matter. You don't need to put that underline in there. Okay, so hopefully I've unpacked all of that now. We're talking simply about regular transition matrices. We're talking about applying them to an initial state vector and to lead to a stabilized system if we've got a regular transition matrix. Okay, right, I'll leave it there. So obviously 9G next. Good luck with your practice there, and thank you for listening.